Well, hello and welcome. We've got Henry, the noble mouse, the water wheel, and Gertrude, the selfish cat. We're going to see how Trig, trigonometry, cosine, can save Henry from the selfish cat. So let's get into it, shall we? Here's our situation. Henry, he's a king among mice. He shares his crumbs with the less fortunate, even if he's hungry, and on his mother's birthday, he brings her flowers. He's a good guy. On the other hand, there's Gertrude. She's piggish and selfish, and she's fed daily by the good farmer, Farmer John, but despite a full belly, all she wants to do is kill and eat Henry. Henry, though, he's clever. He escapes the cat and jumps on a water wheel. Now, hating water even more than Gertrude hates Henry, she just decides to wait. She thinks maybe Henry will drown. Henry, though, he can hold his breath for 45 seconds. That's pretty mighty for a small little mouse. So the question is, will he survive? All right, so what are you going to need to know to figure out this question, first of all? Pause the video. Think about it. What information do you need to know? Now, if you'd like to do this on paper and follow along with us, if you look in the description, there's a link there that lets you download a handout to kind of pace you right through the whole thing. But in the meantime, here's what I think we're going to need to know. Are you ready? If you haven't thought about it yet, go ahead and pause the video. Here we go. We have to know how long Henry's underwater. We have to know how fast the wheel's spinning, how tall is the wheel, how tall is or how deep is the water on the wheel. We don't need to know the total depth of the water, but the depth of the water on the wheel we have to know. So we're going to explore all that right now. Let's get into these details, shall we? All right, so here's our situation. Henry's height above the center of the wheel is modeled by this function, h of x equals a cosine bx plus d, where x is measured in seconds. So the height is y, x is in seconds. That probably doesn't make a whole lot of sense. I'm going to take a couple minutes and explain how all that works here in just a moment. In the meantime, though, we're given the fact that the water's depth is 3 feet below the center of the wheel. Takes 3 minutes to complete a full revolution on the wheel. And the lowest point is 5 feet below the center of the wheel. And that takes 90 seconds after being at the top, right? All right, so take a guess. What do you think? Henry's going to survive? Henry's not going to survive. Do you like this question? I do. I don't know. Let me know what you think. Before you do the math, is Henry toast or is he going to make it? All right, now let's see how or why cosine models this function right here. So there's time is transpiring, time's going on, right? And as time goes on, his height is going up and down. You can see that by the green dot right there. The height above the center. It doesn't matter how far left or right he goes as he's going around the circle. We're only worried about how tall, how high above or below the circle he is. So the x-axis is time and the y-axis is the height. Now, we know that at the beginning, he's 5 feet above the wheel's center, and after about 45-ish seconds or so, it looks like he's the same height right here. So here, let me turn that video back on for us here. There we go. So we know that after 45 seconds, he's about the same height. At 90 seconds, he's at the bottom. Before that, around 65-ish seconds, he hits the water. 90 seconds, he's at the bottom, and he comes out, looks like somewhere around 120 seconds. So what we've done is we've taken this circular motion and put it on an XY graph, where the time is x and the height, well, that's the y. So you can see right here that as the wheel goes around, his height goes down, hits the minimum, then comes back up, and it just keeps repeating that. And that's why if you stretched out this function infinitely to the right, it would just keep repeating the same exact pattern. So yeah, that's kind of cool. So time's going on, right? Mouse goes around the circle, right? As the mouse goes around the circle, the height is changing. So x is time, y is height. Trying to show you one more time in case you don't see it, but that's how it's working right there, right? So the green dot, that would be the y coordinate. The time is the x coordinate. So if we map that out on an xy plane, this is exactly what would be happening. Starts at the top, goes down, hits the bottom at 90 seconds, comes back up at 180 seconds, hits the top again. All right. So here's our first question. We have to unpack what this function is and what it means in order for us to figure out if he's going to make it. right? We have to figure out if he's going to live, so how long is he under the water? So to do that, we have to figure out the amplitude of the function, the period, and the value of d, the midline. So let's go ahead and explore that. Once you pause the video, try it on your own, and then come back when you're ready. All right, so amplitude, right? That's the distance above or below the midline. The midline is at 0, so it looks like it's going to be 5. There's another way to find amplitude. You can take the range, divide by 2. The range, well, that's 10. 10 divided by 2, 5. Either way, amplitude's 5. Let's talk about the period. The period's pretty easy. Maybe, though, sometimes you can't see it. From one maximum to the next, sometimes it's hard to see what those numbers are, so you can just drop that whole distance down, and then look, it goes from 0 to 180, so that's a 180-degree period. All right, so now we know what the amplitude is, we know what the period is, so let's find A, B, and D. Well, A is the amplitude, so it's just 5. B, we have to do a little bit of work. There's a formula, 360 divided by the period that we counted, so 360 divided by 180, B is 2, and D is the same as the midline. So since the midline is 0, D equals 0. So our function is h of x equals 5 times the cosine of 2x. Pretty cool. All right. Next question. It says, show that Henry is first submerged at 63.4 seconds. That can be a confusing question. The reason these kinds of questions are asked is that sometimes figuring out this number is really tricky. And sometimes if a student messes that up or doesn't know how to do it, then the rest of the question is lost on them, and it can absolutely destroy their grade because they're not able to properly show what they actually know. Maybe because they just made a simple mistake, or maybe because this one just stumped them. Sometimes that happens. So this kind of question gives you the answer, but you have to show how you would get it. So the way you do it is you just pretend like you didn't have this answer, and you go ahead and you say, hey, at what time, after how many seconds did he first hit the water's surface? And then you do the work and you find that answer. All right, so here's what we know. We know that the water's surface is 3 feet below, right? And so that means that the h of x is going to be equal to -3 because 3 feet below the circle center, right? That's h of x. So here's our function. We're going to plug in -3. And we got to do a little bit of algebra. Just divide both sides by 5. And then we've got some trig to do. So this is going to be done in the calculator. We have to take arc cosine of both sides. Takes the ratio. -3/5 tells you what the angle is, right? 126 point blah, 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 blah. Now, don't round that yet. Don't even write it down. Just leave that on your calculator and just divide that by 2. And then you write down this number because that's not going to be your final answer. It's not rounded, but you show your unrounded answer. That way, if you do make a little mistake, you can still get a lot of credit. So rounding to 3 significant figures, we found that, in fact, we did find 63.4 seconds is the time at which he first entered the water. So now, how long is he underwater, right? If he's underwater for more than 45 seconds, we're in a little bit of trouble because Henry can hold his breath for 45 seconds. So is he going to survive? Let's see. Can we figure out how long he's underwater? Go ahead and pause the video and try it yourself. And then when you're ready, come back. We're going to get into it now. All right. So Henry is underwater from 63.4 seconds until what? Right? So our function is 5 times the cosine of 2x, and we have this of h of x equals -3. That's the water's surface, right? So how are we going to figure this out? There's actually a pretty simple way. We have to find that point right there. And the fact that cosine is very symmetrical. We've got some symmetry going on here, and it's cyclic. It makes things easy for us. So check this out. That's 63.4 occurs right here, 63.4 seconds after 0. That means that this one is 63.4 seconds before the next maximum, which is 180. So if we just take 180 and subtract 63.4, look what we get, 116.6. So our coordinate right here would be 116.6 comma -3. So now, how long Henry is under the water is the distance between here and here. So we just have to subtract, and we find out that, 53.2 seconds. Doesn't look like he's going to make it. Got a mouse funeral in the future. But don't despair. This is fiction. We can dream a better dream. So let's say we're able to change the depth of the water without worrying about it changing the speed of the wheel. So we can just lower this level so that he's underwater for 45 seconds. So what's the maximum depth of the water on the water's wheel that Henry could survive? Let's go ahead and see if we can set that one up. Why don't you try it too? Go ahead and pause the video and then come back when you're ready because we're going to get into it right now. You ready? All right, so we're trying to figure out how deep does the water need to be so that when it enters the water and it comes out of the water, only 45 seconds have transpired. Well, here's what we know. We know that at the middle right there is the bottom, and that happens at 90 seconds, right? That happens at 90 seconds, and so we're going to have half of that 45 seconds before the 90 and half of it after. So we can just divide both by 2 and get 22 and a half, right? So from that 90 minus 22 and a half, dang, look at that. 67.5. Now, here's the part that's a little tricky. Yes, we need him to hit the water at 67.5 seconds, but the question is, how deep is the water? And our function doesn't tell us the depth of the water. The function tells us how far below the center of the circle or the center of the wheel is the water's surface. So let's zoom in on this and take a look, see what we got going on right here. So we have the water level right there, and the function tells us the distance from the center of the wheel to the water surface, but we're curious, how deep is the water on the water wheel? Oh, yeah. So we know that the total distance is 5. Let's go ahead and clean this up a little bit. What we're going to do is we're going to plug in our number, right? 67.5 seconds into 5 cosine times 2x, right? And we're going to get negative 3.54. So we're going to see that the water's surface is 3.54 feet below the center of the wheel. So since they both add up to 5, we're just going to subtract, and we find out that the water is 1.46 feet deep. So that's the most it could be. If it's that deep, it's going to take 45 seconds for the wheel to go through the water. So the mouse could just barely hold his breath long enough, come out the other side, hanging on for dear life, but he'd be all right. Now, there's one other way that we can change something and save his life. So let's say that we can change the speed of the water, the currents. We can change the current speed, and then, maybe we could speed it up a little bit so that he'd spend less time there, right? Because the faster the water is, the quicker he's going to go around. So what's the lowest speed that would be fast enough so that he would be underwater for just 45 seconds? Right? Assuming that the wheel changes speed exactly proportional, like directly the same as the speed of the water, right? Well, go ahead and pause this one and then try it on your own. And when you're ready, come back. We're going to go over it right now, though. All right, so this is a distance equals rate times time question. Now, the distance that we're really interested in is shown by this little arc right here, this arc length right there. To find that, we first need to know the circumference of the whole circle. Since the radius is 5, 2 times pi times 5 is 10 pi feet. So the entire circle is 10 pi feet. Now, what about the part we need that's just underwater? Man, there's a couple ways to find that. I think perhaps the easiest way is just with a ratio. We know that a complete circle, 360 degrees, one complete revolution takes 180 seconds, right? And we're told that the amount of time it takes for the wheel to be under the water is 53.2 seconds. That's how long it takes from here to here in time as it's rotating. So all we got to do is set up our ratio like that. Now, if you double 180, you get 360. So in order to make these equal, we just have to double it. So 2 times 53.2 is 106.4. So our angle is 106.4. So to find that arc length right there, we're going to divide 360 by this because that's the portion of the entire circle we have. So we have 106.4 out of the entire thing, and the entire thing is 10 pi. So this times 10 pi, 9.29 feet. So now we have our distance, right? Distance equals rate times time. We know that our time needs to be 45 seconds, so we're going to divide both sides by 45 seconds and get 0.206. Hey, I think this was a cool question. I hope you had a good time. I know I really did have a good time putting it together. I hope you learned something about how those trig graphs can model circular motion. Hey, if you did, give it a thumbs up, like, comment, share, all that kind of good, happy stuff. Until next time, vaya con Dios, compa.